Yeah, just tell me when to go.
Yep, all good.
Awesome. Okay, tell me when you get my screen, and so we can get started.
Yep, I can see it.
Nice. Oh no. Okay. Uh, nice. Okay, so well, guys, and everybody who's watching the live stream or will watch later. Hello, and welcome to the ACL and Message Authentication Deep Dive talk. I'm Enrique. I'm one of our One engineers, and basically, here we will talk about something that may sound very ethereal with the title, like very strange, but actually, with experiments that we have been doing lately, and with the release of API DAO profiles, this came up, and it's actually a very powerful pattern that we would like to share with you. We will talk about the ACL itself, this contract. The ACL is one of the parts of Argon OS, and it's a very important one. You will shortly see why. You will see what is message signing, and basically all the shenanigans that can come up with this, and all the good things that come with message signing, and how this can be leveraged then, both the ACL and message, for off and on-chain verification. So yeah, you can see the agenda here. So first, let's talk about a bit about the ACL. And so I have a LA5 doc here. We're not going to read through all of this, but basically, let's have an introduction about the ACL to really just get into context. And so first, basically, as I said, the ACL is just one part of the whole Argon OS. But of course, along with the kernel, it's basically the backbone of your organization, as it's basically the thing that allows you to know if you have permissions or not to execute something on the Argon client, or if you're using the wrapper or on some place. That's basically what allows you to execute an action or not in the organization. Say you got an organization like this and you wanted to perform an action. The ACL will have all the permissions inside of it. We'll see later how they're actually stored. And so, for example, here is basically the first way you can see the permissions themselves. If you saw the permissions talk given on Wednesday by Brett and John, you'll already know something about these permissions. But basically, what they say is that some entity, let it be an account or another app, can actually perform an action. So a permission is composed of some stuff, as we can see here. We can actually see that a permission has an address, an app, a role, and some parameters. We won't dive deeply into these parameters because this is a very deep rabbit hole, but it's there. And so with that, with these three things, the address, the app, and the role, we can actually say that a permission is basically like bundling these together and forming a unique key. So with this key, we can actually check for permissions in the Acl contract. And so after we got this key, we can then just dive straight into the Acl contract to actually see how it's laid out. And then we'll go through the flow of checking for permissions and actually creating permissions, and see the little gotchas that are there. So jumping to the contract, this is the actual ACL contract. You can see, let me zoom out for a little bit, don't worry, I'll do it again. You can see this is the whole contract. Of course, it's not the smallest contract, but actually it's very easy to read once you know your way around it. So first of all, the nice things about not only the ACL, but all of the Argon OS contracts is that usually they follow a very simple structure. You have all the constants that you need to declare for the contract, the mappings and the data structures, the events, then function modifiers, then the functions that are exposed in the contract, and later down below, you actually get all the internal functions that are actually used to interact with the chain and the contract itself. So having that in mind, we can actually see that first, the ACL follows a very, very interesting inheritance structure, but we can totally just abstract this away and focus on what the ACL is actually doing. First of all, I want you to have in mind that, by the way, Brett, you can see the code clearly, right?
Yep, it's really clear.
Awesome. Great. So first of all, I really want you to have in mind this. There are special roles and special addresses on the ACL itself, so it can detect how to do stuff. By far, the most important role, and a role is something very abstract, but basically it's like the name of a permission. Like if you wanted to manage a profile, there will be a manage profile role. And this role, you can actually see this, it's this long hex word with, you may be like, why isn't it string? Well, strings in Solidity are a bit difficult to handle. And so this was built with the keycache hash of that string. They create permissions role in this example. But you can also build these strings by just like doing the keycache hash of the role you want to create. I have an example here with the Remix editor. And so as you can see, I can actually, for example, just declare a constant and say like, okay, I want to create a manage profile role. So I'll just like do the keycache hash of this. And then of course, if I deploy the contract, I can just call the function here, manage profile, there we go. You will actually see that the role is returned here as with the keycache hash. And so that is what's happening here. And so that is why the explanatory comment is up ahead. So you know what this is? It's just a keycache hash of the role itself. Then we got opcodes. We're going to skip this for now because these are part of the parameters, and we will not go into this, as well as the params. And so these are some internal constants that are also used on the params themselves. Again, we're going to skip those. You will see that we will skip quite a lot of stuff here, but it's actually because for evaluating different parameters for a permission, it's actually pretty involved. And if we went deep into this, it wouldn't be basically a dev workshop, but actually more like a course in ACL engineering. And we don't want that. We just want to know how to leverage the ACL to actually use it for on and off chain verification. And so you can see that this constant is very important. And so you will see that it's defined here. It's the keycache hash of this, a empty, basically 0 UN256. And so it results to this. You'll see how it's used. This is also pretty important. And basically this is the no permission address. When we go into the diagram that I showed earlier, you will actually see how this is used to actually determine if an entity has a permission or not. This is the any entity address, and this is the burn entity address. We'll see how this looks later. Of course, we have errors. We can skip this for now because we won't actually do something that will basically make the ACL explode, so that's fine. And so here we got something interesting, which are the mappings. The mapping is basically a structure that if you had to visualize it, will be something like this. This whole thing, you could basically see it as a street with some addresses that then resolve to a house, and a house can have a key inside of it. So yes, this is the permissions, exactly how they will look in the contract. So this permissions is actually just this mapping. The permission params is something that we will not see because again, getting to know how params are resolved can be more like ACL engineering. We don't want that, but you'll see. And also, we got another mapping to see who's the manager of a permission. And of course, here we introduce some concepts that you really need to think about. First, what's a manager? You get a permission, right? A permission, we will see that it has, again, an address, an app, and a role. Basically, who is the entity that is allowed to perform this action? Where can he perform this action? And what role is actually this action? And so, with that, we will be able to see that the manager is basically the person that manages these roles and can revoke them or assign them to an entity. Again, this is very important because basically this is like the boss that is managing the permissions that he can manage, that have assigned that person as the manager. And so we got some events here: set permissions, subpermissions params, and change permission manager. These are important to know that they're there if you're doing some even listening on the Acl contract, but they will be as relevant as for this workshop. Then we got the modifiers, as I said. First, only the permission manager. If you don't know what modifiers are, they're actually really simple, even if Solidity can seem a bit daunting at times. This is just saying, hey, the person that sends the transaction needs to be the permission manager for the requested app and the requested role. If not, we will see an error. And again, no permission manager. This means that the permission manager for a certain app on a certain role needs to be basically this address of 0, which means no one, basically. So if this happens, it means that there is no permission manager. And so if you use this in a function, let's say if you want to perform an action or modify this action, if you have the no permission manager, it means that basically this permission that you're managing or this action that you're executing should not have a permission manager. You'll see how these are used later. So the ACL initializes here, and something pretty important that you can actually see in the ArgoNOS reference is that the ACL, when an organization is created, is actually instantiated along with the kernel, because it's a very important part of the organization. And because if you didn't have an ACL, basically the whole organization will fall apart, because you won't be able to resolve transaction paths to do something, or you wouldn't be able to actually see permissions, And so the whole governance structure of an organization will fall apart without an ACL. So, going a bit further, we can see that the only very important part about this initialize function is the fact that first, it needs to be initialized by the kernel. You cannot initialize it yourself. It needs to be through the kernel. And then this actually creates a permission of permission creator. And then this is the address. And then the create permissions role that we saw earlier. So basically, this is creating a new permission for these parameters. And we will see how this works below, because we actually have to know how this function actually works so we can actually understand this thing. But keep it in mind, this is very important. So we can see this is the external function of create permission. I could totally call this, or the voting app, which is actually the app that usually gets the create permissions role. This is very important to keep in mind, and this is why usually to perform actions on a organization or to create a new permission, how we're going to do later on demos. The voting app is the app that actually gets this permission. You'll see later. And so you can see that here you need an entity address, an app address, a role, and a manager. This looks really familiar to this structure here. But basically, the who is the entity. Basically, who is allowed to perform this action, which app or which account, which entity. In which app is this entity allowed to perform the action, and also the role. The role, again, remember, is the kick hash of the string that defines the role. And then we need to assign a manager. In most instances of creating a permission, you really want the manager to be voting. So it's actually able to be modified, and the management of this permission is not centralized. If you assign, for example, an account as the manager of a permission, basically the manager of this permission, it's not democratic anymore, because a single person we have the say of like revoking a permission or basically removing the manager himself or passing ownership of it, which can break your organization if you have a malicious issue. You see that it's marked as external, so this can be called from outside the contract. See, auth create permissions role. This is something used by Acl Contracts, this app modifier. So basically, what this means is that the person that calls the contract here in the external function will need to have the create permissions role. Now, this is the first point that we can connect. How am I going to call this function that if I need this permission? And this is where transaction pathing and voting comes in. With transaction pathing, we can find a path that we can call this function with. And so the key thing here is that the voting app, as I said before, gets the create permissions role. And so if the voting app has it, the voting app can actually call this permission, can call this function and actually execute it. This is very important, and it's why you want the voting app to get this role. So it's democratic, and also you can actually create permissions without depending on someone else. See, like this is granting the permission, basically giving the permission to someone else. And here you say, hey, which entity do you want to give the permission to? And which app do you want to give it to? And what's the role you want to give it to? And then this will call another function that is marked as external. But as you can see, the only difference here is that it has a params method, a params argument. And so this params argument, if it's passed empty, you'll see that it will be given then the empty params hash in this ternary expression here. It's checking if a permission will get any params that will need to be evaluated. Of course, we said that we will get into this, so we can think of, as of now, we can think that the params hash will always be the empty param hash we saw above. And then, this calls the internal function set permission. Remember that internal functions of the contract are actually set with this underscore, so it's easy to read and easy to know what's going on. And you will see that this eventually will set permission on the entity allowed, the app allowed, and the role given with the empty params hash. We can then also revoke a permission with the same parameters. And you can also see that we get the no permission concept here. Keep this in mind. When we actually go to the flow of getting a permission, you will see why. We can then set the permission manager, remove the permission manager, and some functions that we won't cover here, like create burn permission. We'll just talk about burning a permission later. Also burning a permission manager and whatnot. Now, but something really important here is this function here, get permission manager. This returns the manager of this permission. And so the ACL has something interesting right now. The ACL doesn't expose a function to know if a permission is created or not. But by getting the manager, you will be able to figure this out. You will see how later, when we actually go into examples on how to create a permission, set managers, and then access Web2 assets with Web3 verification. And this is a very important function that actually the kernel replicates and just calls the ACL has permission function. You'll see that this is really similar to the structure of this diagram. As you can see, you need a who. Who is the entity allowed? Where it means in which app can the person perform this function, perform this action, and on what? So again, we got bytes memory how, but remember, how, this is the param section. We will get into this. And so basically, we can actually just ignore these because we will actually assume that we will have no params evaluated. Again, we don't want to do ACL engineering. We just want to know how to leverage it for this whole ACL and message authentication. So here you can see that it calls a has permission function again, but with one of the inherited contracts is conversion helpers, and it will cast these bytes to a new int array. That is because the params, they're evaluated by basically integer, This is why we have opcodes in a enum. But don't worry about it. Just assume this does not exist for now. So you can see here it starts to get funky because you can see you have the has permission. This is what was called up here. But you get now the who params and you access the permissions mapping. Again, by combining the who, the where, and the what, basically the entity, the address, and the role. And how does this happen? Because when reading the contract, this can be really disconcerting. Basically, what is happening is this: you get the who, the where, and the what, and basically this params hash function. What it's doing is just the keycat hash of the concatenation of these params, the who, the where, and the what, in that order. We will concatenate who, where, and what, get the keycat hash of this. And then with that unique key you just got, because it's a hash, you will then access the permissions mapping and see what's inside. Now, this is the first thing we need to explain. Usually, when you think of the Acl allowing you to do an action or a permission, you think of something like, hey, this will probably be just a mapping that will have like a true or a false boolean inside of it, and if you can perform the action. Well, that's not really true. So that we can have more flexibility with the whole param thing for verification with certain rules, it was actually decided that we will basically keep words inside of it. And so this is where the empty params hash or the no permission hash, or basically custom parameters, if you want to get into that and pass it into the function, comes into play. What indicates that there is no permission, or basically that a certain entity or a certain app with a certain role, if it has the permission of not, if inside the permissions mapping with the unique key that you just got, is it returns no permission. No permission, again, remember, this is the bytes 32 0. You can actually visualize this no permission thing as a string prependent with 0x and it has 64 zeros. And so if this comes up, basically, if you get in the who params no permission, the Acl will say, hey, you don't have the permission to do this. So it will just stop evaluating this, and then we'll go through the other cases. Of course, we can actually see that it's actually also evaluating params, but of course, we can actually just assume, as we will always have an empty params hash, this will just like evaluate it true because it has no rules to comply to, and therefore, if the entity has the permission to do this, it will always be able to do it. Now, basically, you can see if this is true, if this whole expression is true, the Acl will say, "Hey, you do have the permission." But again, it's good to remember that with the key you access here, you will actually get another key back. This key that you get back is either a no permission or an empty params hash. Basically, that means that the user has permission, but it has no rules to comply to. And so here we get basically very deep into the whole evaluation of the params. And again, we won't get into this, but just so you know, so what params can actually do, what is really important is that params allow you to implement complex conditions like time blocks or waiting for a certain block number before you can actually perform an action. This is still possible because of the code evaluation that happens basically along here, which gets really crazy and actually allows for some very interesting functions that the Acl has that people don't really know about. If you saw the live stream on Wednesday, you actually got to know that there is something called Acl Oracles. And basically, these Acl Oracles are made possible because we have parameters with opcodes. But this is a complicated topic, and really, not that many of the apps actually take leverage of this. One suite of apps that actually just push the limits of this to the maximum is the Dandelion template. This is also why the Dandelion template it's a bit more difficult to check the permissions it has because it has to evaluate parameters. And you can see here you got a bunch of functions that just evaluate logic. So we won't get into this because it will then basically turn into a low-level language course that is basically here. Again, as I said, you can be an ACL engineer full-time. This is why we call people DAO architects. But yes, this is the whole contract. You see that there are some basically some key functions: has permission, get permission manager, and also the create permissions itself. But now, basically, after all of this, we saw the contract. We more or less know its structure, and it has the permissions params. Let's see, actually, okay, how will I do stuff? And first of all, again, let's go to this diagram. If you wanted to check for a permission, let's say you yourself, you wanted to check for a permission. First, you need your unique key. This means doing the key cap of your address if you're acting with an account. Basically, okay, this is my account. I will just copy paste my account and then concatenate it with the app that I want to act on. Basically, where do I want to execute the action? I will just put it there and code it. And also the what, basically the role. And remember again, the role is the kick hash of the role string itself. So you will put these things together, call this function abi.uncompact, which of course it concatenates it. If it does a little bit more than that, it actually does some encoding into a non-prefixed hex string, but don't worry about that. It basically just turns everything into a hex string, concatenates it together, and then that concatenation will do the key hash of that. So this is going to be a unique key. With this key, you can go to the permissions mapping here and actually access the corresponding part of the mapping. And so you can see here the mapping that you get, for example, no permission, no permission. Again, remember, no permission is the address with prefix with 0x and 64 zeros. Let's assume that this is a no permissions address. And you can actually see these are the first characters of the empty parent hash that we can actually see up here. And remember what we say. If we find that the key that is returned from the permissions mapping is this empty params hash, it means that we actually have a way to perform this action. We have the permissions necessary to perform an action. Now, this is really interesting because the ACL is a very powerful thing to use. But in the end, this gives you a lot of flexibility. For now, and for the sake of simplicity, we will use the ACL as basically a Boolean structure for checking if we have permission or not. We're not going to do complex permission evaluation. But basically, this is the flow for checking for permissions. Of course, in reality, we'll need to use some heavy piece of machinery, which is actually the contract. The Argon wrapper. Of course, this will be made easier with the toolkit that we have a request for comments basically right now out in the forum. So if you want to check a bit of that, then go to the forum and see what's up with the toolkit. We're building it to make it easier for you to implement things like this. Now, we got this flow for checking for permissions. Grab your stuff, get your key, then see the address, see the actual permission mapping slot you're going to access, get back the unique key that is inside, and check if it's either no permission or an empty premise hash. This is how you know you have permission. So now, you got that flow down, right? So let's talk about some things to have in mind before we pass on to the other part, that is actually the Web3 message signing. First of all, remember the burn addresses that we saw around here? Yes, the any entity and the burn entity. Now, this is important to keep in mind that any entity corresponds basically only for grantees. So this actually means that this address only corresponds to the grantees of a permission. Then, why does this matter? If a certain role is marked, if a certain permission exists with any entity allowed in the whole param, it is not applicable to the manager, but only to the whole param. It means that basically any entity will be able to perform the action. This is a special address that the ACL recognizes for this purpose. So if you use this to basically, in a naive way, to allow only that address to use that won't be possible and will actually make that permission and that action be able to be executed by anyone. So it's pretty dangerous, and you have to know how to use it. A good example of where you will use this is it, for example, you want to create a DAO where literally anyone that has a Web3 account can create a vote. In that case, you will say, okay, I want to create a permission of create votes on the voting app. And as the entity, I want to set it as any entity. Meaning, okay, I want everyone to be able to create votes. They don't have to pass through a complex system of evaluating if they have permission or not. We just want to be able to let them create the vote. That's where we will use the entity. And so the burn entity, it's actually corresponding to managers. And of course, this may be hard to realize at first when we get here because it says burn entity, but keep in mind this is only for managers. And what does this do? Basically, if you assign the permission manager to this address, this permission will never be able to be changed again. So basically, it's effectively a way to freeze a permission over. And so let's say, for example, if you want to give the create permissions role, let's say to yourself, right? So you give that permission to yourself, and now you can arbitrarily create new permissions. But now you will also, if you also set the manager as burnt, it means that basically you will have the power to create permissions forever, and you will not be able to change this. And if you one day just disappear from the organization, that organization will not be able to create more permissions unless there exists another permission that allows another entity to actually create new permissions. So basically, do this if you want to freeze a certain permission. Do this if you want to allow anyone to perform the action on the organization. And so with that in mind, we saw what we need from the ACL. We will release this document later so you can actually very closely review what's happening. But again, the key things to take away here is that first, the ACL has some pretty important constants up here that you need to remember. Burn entity, any entity, no permission, and empty burn hash. The way to know if you have a permission, you need to access the permissions mapping with your unique key, which consists of your account or the entity account, the app that it's going to be executed in, and the role, which is the gigacache of the role address. Of the role string. With this, you access the permission mapping, and then you'll see if you get a permission back, if you get the no permission bytes word back, it means you don't have the permission to perform this action. But if you get the empty params hash, it means that you have the allowed permissions to perform this action. And so you will be able to execute the action, and you will get the famous signer panel, we get in the client, or if you're using the wrapper somewhere, you can just send the transaction and it will go through because it's legal in the ACL sense. These are the key things to take away from. Now, let's get into something else, which is a bit more less clear, which is message signing. And it's because Ethereum doesn't have a good history with this. There are actually many functions that implement message signing. And so we can actually see that first on the ACL. Let's get some examples here. Yes. Here, first off, a message is really it's basically just a string of data, which is then signed by your account. Let it be public key or private key, depends on how you implement it. You want to use the private key, and we will use the private key here. Fortunately, Web3 does expose pretty clean methods to do this without basically alarming the user and actually keeping it secure. But you still have to take into account some stuff we will talk about later. And so this message is signed by the private account, and basically, before actually signing it, you need to prepend it with a certain special message, and you will see why now. So let's try this examples of signing. This is from Dan Finlay, which has worked a ton on this and actually has written a few articles in this. And so here I have an account with MetaMask, and I'm connected to Rinkeby. But the reality is you only need an unlocked account to sign a message. So we will try some of these, and I will explain the differences. The first one is eth.sign. Now, let's click it. Does the pop-up is visible, Brent?
Yep.
Amazing. Okay, so first of all, if you see this somewhere and you see this message, I do recommend you not to sign this. This is very alarming. And on top of this, this message is non-human readable, and that is bad. And of course, eth.sign was the first method implemented for this, for the Web3 library, and has since personal sign came out, has been deprecated. It only exists because Web3 is kind of slow to properly remove things from the library, because there are a lot of sites that are still depending on this to actually work. But what this does is basically, we can trust this site. It's open source, so we'll just sign it. I will open my console. And you can see that this is the message that we signed. We get this, and so we also get an object message. Right. Sometimes I can just deny the signature, and we will get that error. Yes, but of course, this is the thing that we care about. This is how the message looks signed. You can see it's totally different from what appeared. And so this is, again, composing a prefix that is particular to the EIPs that defined this whole message signing thing. And this is signed with your account's private key. So this message basically proves that it's you. Now, this will lets us do powerful things later, but let's see the other ones. As you can see, personally, I will tell you, do not use eth.sign because it's old and it's deprecated, and you don't really want to depend on deprecated things that could be removed any moment from the Web3 library. Now, let's see personal sign. You can see this looks way better, right? You actually get a human readable message, and there is no huge red warning here, which is amazing for us. And so as a user, I can totally just oh, okay, nice responsiveness, MetaMask, okay. And I can then just read this message and see what am I signing. The good thing about this is that this whole window is abstracted by MetaMask. So that button itself does not have a way of injecting some text in here and me signing something else. So I will sign this, and you will see that first I get an alert that this actually verified me as a signer. with my account. You can see 0x5790D, right? If I open my MetaMask account, you can see that this is actually my address. And so that is the cool thing about personal sign. Even though you can recover the address with eth.sign, personal.sign is a much more transparent way of actually signing a message. And at the same time, there are both third-party libraries and a library built into Web3 to actually recover the address that signed the message. And that is amazing because it lets us basically use message signing as a way to verify that the user has control of this account. And this is a very important key point. And the reason why is that basically using the ACL for verification is very good. We just need to do a call to the chain, and the ACL will say, okay, this person has actually permissions or not. But if you guys have used Frame before, I can actually add an account that is an arrogant DAO. And so in that way, I can actually act as the agent of an organization. This means that even though I will be using a certain Ethereum account to send messages, for the ACL and the address that I will return to the ACL will actually be the agent's address. And that is the problem here. You can actually make fake extensions that return a certain address to those methods. And so people are basically able to just fake you having your address connected and just call the ACL with that. And if you're in a website, you're using basically a permission to let a user access, let's say, a picture, for example. I could just make a little extension that returns a random address that actually has a permission, let's say Brett's address. And so if we actually just call the ACL with that address, then it's done. I will get to see the photo because I faked that I was Brett. And so the way to avoid this is to implement message signing. This is again really important because with a signed message, your public key is actually tied to this. And so with either personal.easy recover or another third-party library used to recover the address, I can actually get the address back and say okay, this is the address that this person returned, and this is the address that actually signed the message. This means that if the addresses match, then it means that, hey, this person is actually themselves. They're not being attacked. And so I can actually display the picture that I want to display and be sure that a non-malicious user actually got the picture instead of an attacker. Of course, there are some gotchas to this, and there are some ways you can actually reinforce this whole message signing thing further. But this is a very important thing to have in mind. This is the whole pattern. Checking for permissions in the ACL and signing a message to then recover the address and compare the two addresses. And if they're equal, this person actually has permissions. Now, we have some more methods to test. Personal easy recover will again tell me to sign a message. We'll recover the address. You can see it actually recovered the signer again. You can see it's my account. Now, what's happened? You can see this is Dan Finlay, and so don't worry, we won't read this article, but you can see that personal.sign was implemented way back in 2017, at least the RPC method of it. And so, since then, you actually have an even newer and even better way to sign messages, and it's called scaling with 3 sign type data. You can actually see it here, sign type data. Now, this article is really recommended to read because it exposes basically what we're doing. It talks about using this message signing technique to protect Web2 assets along with Web3 verification of message signing. Basically using cryptography to actually protect the data that we want the user wants to get. So as you can see, this is actually the post with the latest standard for signing. Of course, you can still use the other two. And in fact, in the examples, for the sake of simplicity, we will use personal sign. So let's see how sign type data looks. Nice. You can see here, MetaMask says you're signing a message, hi Alex, and then a number. And you get, of course, the very best number, which is lead. And so I can sign this, and you can already recover the signer address. This is very good because it's a very clear way to expose to the user what you're signing and what you will do. See? Either mail. So basically, these are ways to do things now. And so the cool thing is that you get then basically three methods. And to recap, please don't use eth.sign, because if it was me using your site and I actually saw this message, I wouldn't sign it. The security concern with eth.sign, which then Finlay actually exposes here, is the fact that you can actually, like in this very long PR, you can actually see how, if you go through the whole conversation, you will see that it's very insecure. And people can actually use it to sign transactions on your behalf. And basically send those transactions to the blockchain. This is really dangerous because it means that basically, if a person recovered this with eth.sign, it could then just make you sign a message, but it's actually a transaction that will drain all of your funds. And then with just an innocent message that you didn't know what was in there because you weren't able to read it, you just got hacked. And so the way to avoid this is to either use personal sign and personal sign type data. These two are fine to use, but of course, it can be that pretty, right? There are actually some gotchas when it comes to actually using these ones, because depending on the node that you're communicating with, they will actually have implemented either personal sign or sign type data or both. Luckily, if you can call it that, MetaMask, if you didn't know, uses Infura in the background. And what does this mean is that Infura can actually just detect the RPC call that you're doing and just say, okay, I need a node that can actually parse personal sign, get the RPC call and resolve it, and then just give back the good thing to you. And so Infura will intelligently do that and relay you to a node that actually can do that. If you use sign type data, Infura can do that as well. But of course, if you're running your own node on your own infrastructure, you have to make sure that you actually get those methods implemented. As far as I know, Geth and Parity nodes actually have personal sign and sign type data and eth.sign implemented. But if you're using another client, you have to check, because it may be possible that this is not implemented and then this will not work. Of course, the good thing about personal sign is that if we actually go to if we actually go to this Stack Overflow answer, you will actually see that with the documentation, you can actually just use personal design and just sign locally. So this method actually can work locally without a node. This is good because basically you can just manage your private keys yourself, sign your message, and be sure that it has not been tampered with and will not send something malicious to the user. Of course, we will go through all that trouble, and we will trust Infura for all the examples that follow as of now. Again, this is the documentation for the docs, and you can actually see that there is warnings for sign or whatnot. This is the personal sign, and of course, this is how you can use it or whatever. We'll actually see how we can implement this in a little bit. But yes, as you can see, this is the actual prefix I was talking about before. with the EIPs that define personal sign type data, they define in standard. And so basically every message will get this string prefixed x19 ethereum site message, a new line, and then the length of the message, the length of the string, and then the message itself. And so with this, it will take all of that and then UTF-8 hex encode it. So you will actually get a hex string, which is what you see in eth.sign, but MetaMask will actually display the whole message before it is encoded. And so that's why you can read personal sign. And you can see, and you can actually read sign type data, because it has a way to parse all of these things before it's actually, before it's actually encoded and sent, either to an inferior node for signing or locally so you can sign it. So this is a good rule to follow. If you're not using a node, you can use a counseled sign, which is one of this one is not on the Danthele example, but again, this is to sign locally, but you can use personal sign. If you had a local account, personal sign is really versatile as well, because you can actually use the password from your wallet to unlock the account. Of course, this can be dangerous as well, so please don't send your password. Your password will be HTTP connections that are not secure, because you can get hacked, of course. And then, if you have a node with an unlocked account, you can use eth.sign, no problem. So, with this, we've seen both message signing and the authentication. Now, we have talked a lot about theory, about like, hey, how do you get a permission, or how do I actually like sign a message? What's involved? But are there any examples live? And of course, yes, there are. I've created this organization, not one high, that is from Luke. I've created this organization on Rinkeby. This is, it's called just EX11. And so basically, if you have been following the news from the Aragon ecosystem, you will see that we actually released DAO profiles lately. And so you can see that we get profiles from DAOs for like Aragon 1. This is live on mainnet. We can just go over here. And you can actually see like, you get, for example, the Aragon 1 profile. You can go in there, you can check it. So this is one thing that is using both ACL verification plus basic signing. We will actually see how this is implemented in a little bit. But I'm running this locally to go through the whole process with you. So first, I'm gonna find my AX11 DAO, which has quite a lot of activity, you can see. And so I will just connect to a 3. Yes, with frame. So I will view the profile. And of course, it doesn't have a profile, so I will claim it. This, of course, will not describe the transaction properly because this is going to be local, but I can then just create the transaction, sign it, and then send it to the chain. So eventually, this transaction will get mined, and a vote will appear here. So what's happening? This is a vote that I created earlier, but you will actually see that, okay, we got the new vote. What we did there was actually use the ACL in the code to actually create a new permission. And we said in the code, we're just basically requesting a new permission, granting myself the ability to perform the action of the role. This is a role that is actually managed profile role. We will see it in the code now. On kernel, so basically we tied this action, this role to the kernel, and the permission manager is voting. So this is totally democratic. I'm not taking over the organization. I'm just gonna say yes. And so this will be sent to the chain, and we need to wait for this to mine. So again, you can see this is really powerful because with the API Explorer here, we actually get the ability to claim profiles and gain permissions to edit them. And you will see now the part of message signing, because again, I could totally just request permissions as a certain address and then just edit the profile if I just have the address faked. But of course, it's not what I want. Of course, this is again the fear nodes. But yes, this is something just weird with the fear nodes. We actually go with yes. So don't worry, this will passed. And so if we get back to the X11 DAO, you will actually see that I now have a profile available. And so, again, if I was faking my address, sure, I could see this profile and I could click edit. But what's the cache? Let's just give it a name, X11 DAO. Let's give it an image. Let's search for something like the logo. This looks good. So let's just copy the link address. And so just put this here, description, the best DAO on Rikubi. And so I'm just gonna give it a link. Let's just link the org itself, because why not? Or in fact, even better, yes, I will actually get a foundation, which is a totally legit Twitter account, right? I will link that. Nice. So safe profile, right? And if you're an attacker, you're saying, hey, this was really easy. I actually took over the organization and actually got the profile, right? Not really. You have to sign the message. You actually get the message to sign. This is the concatenation of the whole profile, but you're actually saying what you need to sign. So I will sign this. Then this got sent to the chain. Got sent to the backend, and the backend verified that I was the signer. And of course, then just updated the DAO. You can actually see that now I'm an editor because I actually verified with my address that I'm the one editing the profile. And we got new links now. And we can go here, like, hey, let's go to the Twitter now. And you can do so. So this was really cool, right? Let's check how it's done in the code. Bear with me. I have to go to my main window. And so we might need to, yes, I might need to zoom a little bit. Brett, you tell me when it's readable.
Yeah, this looks good.
Nice. Good. So the very important thing here is that let me first find the great. Amazing. So we're here. This is actually the code of API. And don't worry if it's a lot of code. I will walk you through it. So we're here on the relevant part of the whole profile experience. This is actually the page that renders the profile. So the very important thing here to see is that first we're using the wrapper. We have a hook to use the wrapper called wrapper, use wrapper here, and we just pass the DAO address that we're looking for. You can find it here as a query string, and so you can get the DAO, init the wrapper, and with the Arium wrapper, you can just get the permission manager, and if the user has a permission. Now, why do we do these two calls? Well, as I said before on the ACL verification, you can actually realize that a permission can probably not exist. And so just calling has permission is not enough because, hey, an user can totally not have a permission, but it's because the permission is not created. And so we need to get the permission manager, actually see if the permission is created. And so if the permission manager returns a string that is basically identical to no permission, which is a string with prepended with 0x and 64 series. If these two strings are equal, then the permission has not been created, and we can just request to create it. And so If not, then you will see that this will return actually the proper manager. And so if it's not the no permission address, this permission exists, and so we can just assume that if has permission is false, then user cannot perform the action because he has no permission. He has to request permissions if it's possible to do so. And basically here's some different, but this is the key takeaway. This is first how you can actually realize if a user has the permission to do stuff with JavaScript. Just use the Argon wrapper, and then probably soon to be the toolkit to check for permissions. Just get the permission manager or has permission. If this true, and so you will actually get to know if you have the permission to do something or not, or if the permission actually exists. Now, there's no more code here, but here is what it gets interesting. So this is the code that ran when I tried to claim the profile. You can actually see that I requested a transaction path. Basically, I just wanted a way to create a permission, but of course, as an entity that has the role has to call this function. In this case, in the org that I created, the entity that has the permission to create new permissions is the voting app. So I just got the address and then say, okay, I want to create a permission, again, with this entity being my account. And on the kernel, which is actually the DAO address, we will allow the manage profile role, which is the gigabyte hash of this string. This is a variable that contains the gigabyte hash of this. And we're going to set the manager as voting. If you want to see, like basically this is called in the ACL. This eventually will just call the ACL function with these parameters. Remember, that we saw it here. This is literally calling this create permission entity my account, the address, the kernel, the role, manage profile role, and the manager being voting. Now, you may be a bit confused and saying like, hey, but why are you actually appending this permission to the kernel? And so the trick here is that permissions usually are tied to Argon apps, of course, because to be able to find a transaction path for them, they need to be checked by the ACL. But the key thing here is that the roles themselves, you can define arbitrary roles. And remember that we're using the ACL as basically a Boolean value store if we have permissions or not. We don't really want to perform actions on the app directly. We just check if this certain role exists and that the entity that wants to perform the action has the required permissions. And so with that, I have to set the kernel as the permission manager. This is an arbitrary decision. I can just set any other app. Of course, you choosing the kernel can be a same choice because this is an app that won't ever get uninstalled from your organization. Let's say you install something like dot voting, and then it comes a time in your organization that this is not needed. And so, if so happens, this actual role is lost. And so we don't want that to happen. We want to be able to visualize these permissions if you actually get them on the registry. And let me just close Keybase real quick. Yes, nice. So we just have to set the kernel because it will never get uninstalled. That is the why. But remember, we just want to know if a user has a permission to do something. This doesn't have to be an action on an Argon app. It can be anywhere. You just want to know if the user has the permission necessary. That is why we're using the ACL as a key value store or for if it has permissions or not. That is why. And we're setting the voting address as a permission manager because we want to be democratic. But of course, I could say hey, no, I actually want to use my account. But of course, we're not bad people. Let's just leave it at this and let the voting address. Of course, then here we do some more validation. But if not, we just send the transaction or the transaction path that I found. And so when this gets fine, it opened the vote that you saw on the Brinky DAO, which is here. And so it will, after this vote passes, will actually get the permission created by the voting app. And so you will have the permissions. Anyway, amazing. Yep, there we go, close votes. You can see. So good. So that's how Apiary did it for the first part. Now, on the edit profile, let's just see this. Let's open the edit panel. Yes, here. So, it's a bunch of verification here. But this is where it gets funky, We're using GraphQL, so on the mutation for basically the graph query, you can see that basically we're composing a message to sign, which is the concatenation of the whole profile. You already saw that in the sender. Then we call personal sign. We're using personal sign on API on this. And then we just say, okay, this is the message that I want to sign, and this is the account I want to sign it with. And so with that, then get the assigned message, and we're just going to send over to the backend both my address and the send message. With these two things, the backend can then say, hey, let's check if these two addresses are equal. It will recover the address from the message and compare it with the address I sent to. Now, so you can see, let's see the backend here, which is completely on the same little repo. So here, yes. So when we switch over to the backend, you can actually see that on the update profile, which is the function that we call to actually edit the profile itself. You can see that we do some things. First, we compose the signed message because you need the original message to actually recover the address. So of course you need to send the original message to the backend as well. And so with that, we can compose the signed message into one single piece, which is the original message, and then we can then just validate the addresses. So this function look for it. Yes. You can actually see that on the backend, we're not doing we're using Web3 easy recover, but we're actually using some functions called some libraries called util and sigutil. These two will let us recover the addresses. And so what we're doing here, yes, first, okay, let's actually hex encode the original message as we exactly saw on the Stack Overflow answer. So, right, we use hex encode this, and this is encoded message. We do this with ethutil, which has some utilities to interact with Ethereum, basically. And so, to recover the address, we do this with sigutil, which has utilities for dealing with signatures. And so we're using the recover personal signature function with the data being the encoded message and the signature, the signed message. So what this would do is just run an algorithm behind that, and so it would return the address that signed the message. And so we just then compare the two addresses. Of course, we're avoiding checksum comparisons here, so we use lowercase a2 and then do a string comparison. And so if this method returns true, then it means that the user did not fake their profile. And so it means that it's actually the user that it's updating the profile, and so we can actually update it. You can see that for sanity checking, we got that the address is valid, and so let's assume that it's valid. And so what we'll actually do then, again, in apiary is used. Check the kernel has permission function, which again calls the ACL has permission function and checks if the user has a permission. Remember, this is the flow that we saw here. It's literally going to do this. It's going to grab the signer address and the address. This is the entity, the app, the role, and the params. And so, going to do this, go packet on the ACL, then access the permissions mapping with the unique key that you got, and see which hash you got. And so, in this case, we get that we actually have permissions. And so, we do have the permissions to execute this action. And so, here is the rail guard. Basically, if this is false, if this returns false, then we'll say like, hey, you don't have enough permissions in the ACL to do this. So here we totally avoid malicious people of actually editing a profile. And so with this, then we just do some database work to actually update the profile. And with this, let's say that it's a bit complicated because there's a lot of things happening here, but with leveraging the ACL for permission verification, if you have a certain permission, and message signing to identify that you're the user, we can actually basically have ownership of Web2 assets like a profile or basically just strings of text or even a profile, even a physical thing. You just need an ACL to work with, which means you can have a permission structure in the DAO for this, and then for every action that requires this sensitive data, you sign a message to verify that the user is properly, like it's not being attacked and it's not being, it does not have an attack that is replicating the address, but it's actually the user itself that is doing this action. And so with this, we can actually go crazy with the things we can do. It's very powerful because, for example, we will totally have, first you can see that you can combine this, like this whole message signing thing and permission. For example, if I had a secret forum and first you need a permission in the DAO to access the profile, like to access the forum. So I can give you that permission. But then, before accessing the forum, I can actually, for example, make you sign a message. I will recover it, and I will basically verify it. And I can basically go further along, and so just give you something like an access token that expires, let's say, in 1 hour. And so with that, we have actually implemented a signing system, basically a login system with no Facebook, with no Google, and no basically other external permission provider. We just need a DAO to set it up, and the user just needs to have an address, and he can have identity built in as we can sort it in the database. And again, he can have the option to not use identity providers like Google or Facebook and just skip all of that and go through into the Web3 world and use this to leverage this whole permission system. Now, this illustrates very well what you need to do if you want to actually, if you need to modify something here, you know? This is the whole flow. But what if you want, let's say, for example, ownership of something? Let's say, like, if there was a super secret set of things that you need to access, but you need to sign a message, and then the backend has to verify it for you to access it. The way to do this is that I will show you in a while because I have to start the servers for these other example. Brett, are there any questions?
No, I do not see any on YouTube right now.
Yes. Okay. So the whole thing here is that, first you did not see that connection string there, but you can just then start the server. Wait, right. Right. Let me just start the server to see if we can show this example. If not, like we can just then do some question and answers. But nice. This actually did start up well. So let's see. Let's see if I'm missing something here. Connection string. Right. And modules. Right. Okay. Nice. So let's see. Here I have prepared something really nice. And as you know, Brad is our CTO. And so we have a list of secret facts that you need permission in a DAO to access. So let's say I'm back with MetaMask again, so we can illustrate the whole process with MetaMask. And so I will enable Web3. And so good. And so I actually do have permissions in the DAO. So with the role set up, so it's going to say fetch. So this is actually going to request a message. So what this will do is actually send this message, which is called fixed white space. I will sign it. Oops. No. Oh, well, that crashed. That's nice. Well, fine. It's good then. So yeah, we can totally show this later. This will be on GitHub. But yes, this is the workshop effect, I guess, for this example. But as you can see, like on the API itself, we actually implemented like this whole permission system for accessing a profile. Like in this very, of course, it's a bit contrived because it's a lengthy process for something like a profile. But you can totally get a super high secure permission system set up with this. You just need an ACL to do this. And message signing. And so yeah, with that we can do some questions, and if not, like this is it. We can just then do a small recap and leave it here.
So YouTube is generally 2 or 3 minutes behind. So I don't think they're going to hear the questions. But we can do the recap and see if there are any questions and do them at the end.
Okay, nice. So yeah, for the recap, remember that the ACL is one of the backbones of the organization, and we can actually use this to create custom permissions on the ACL by just setting it to a certain app installed in the organization and a custom role that is a ticket hash of its string. So with that, we can then use something like the wrapper or the toolkit to actually get a transaction path and create this permission. And so with this permission created, we can then do some verification if the user has permission or not to do this action. And with that, basically just implement the whole permission system for accessing things or editing things. It's fine. Right, so of course, the ACL is not enough as it's not verifying that the user is the one that sent the transaction. It's completely trusting the user to not be attacked. That is fine because the ACL is heavily abstracted away from how it's using the client. We're doing some separate stuff in the client that's basically just working on top of it, on top of the Argon OS part of your organization, and is trying to create and serve permissions. And so for supporting this and verifying that the user is not being attacked and it's not being represented, even if it's actually another person with another account, as we can see, we can actually return an arbitrary address and just like get someone who actually has the permission. And with that account, with that address, access the profile, we can just do message signing and verification to properly verify the user's validity that it's not being attacked. Combining those two things, we can then do complex permission systems, like if we had different roles of the same permission to access further some things further and just like handle these things on the back end, just by verifying the address, verifying the permission, and then giving the user access. And we can also do some other stuff like edit things just by sending messages, by signing messages, and then letting the user actually perform the action he wanted to do that is not on chain. As well as we can take this a step further and, for example, do something like a token access with the message signing. So the user, if it has permission in the ACL and it signs the message and it's verified that it's the user, we can then, for example, just give an access token that expires in some time, and we can totally with that just implement some sign-in solutions that don't require the use of libraries like Google's own signing system or Facebook signing system. Basically, avoiding these huge behemoths that you will never know how they handle this whole identity thing, and maybe taking data from you. You can actually rely on open source code and create a permission system that is open, is reliable, and of course, if you code the things right and take care of some edge cases, you can actually have it be secure. It's not that hard to do. We already saw an example on how to do it. And so, with that, it's basically the whole thing. Leveraging the ACL and its properties of custom permissions to then combine this with message signing and then do authentication off-chain. And that's it.
Awesome. Yeah, I don't think we have any questions on the live stream, but I guess we can suggest where to reach you if there are questions, and then we can wrap this up.
Yes. So my Twitter username is quite a bit complicated, but it's this one. It's CryptoYeezus here. You can see it here. So you can reach me on Twitter. We'll post this later after we finish the workshop. And also, I'm pretty active on the Argon 1 Discord. So if you have any doubts on how to implement this, or you want to know a bit more about it, or just talk about it and some strategies to use with this, I'm active on the Discord. And my username is @Evalir, EVALIR. And so you can just reach me on Discord and I will answer right away any of your questions here. Yeah.
All right, awesome. Thanks, Enrique. Unfortunately, there's any applause, we can't hear it, but I wish I had something to press for the fanfare. But thanks for hosting, and yeah, I think that was a great introduction to the ACL and a lot about the message signing and how we were able to implement the profiles on APRU.
Yeah, definitely. Thank you, man.
For everyone else that's on the stream, we're going to be posting more of these workshops, probably on Twitter as well as our Discord. So keep your ears open, and hopefully you will also join for the next one. Thanks, everyone.
Right.